Hi, everybody. Welcome back to the second session of Chemical Kinetics presented by Anode Academy. Okay, so we stopped with a homework question yesterday. And before moving into the solution of the question, let's quickly brush up on whatever we learned yesterday. Okay, so now let's say that you have a reaction where X times of any reactant becomes product and whose stoichiometric coefficient is y. So we did see that these x and y's are something called stoichiometric coefficients, which we discussed yesterday. And there are three terminologies that we should know, right? One thing is rate of disappearance. Rate of disappearance of whom? Of the reactant. Rate of disappearance of R is simply written as minus concentration changes of the reactant with changes of time. All right. You put a minus sign because whether it be rate of disappearance or whether it be rate of appearance or a rate of reaction, it's always going to be positive. So in order to make it positive, if you take reactants concentration changes, you need to put a negative. This was discussed yesterday, right? And we can also write the expression of rate of appearance of the product. That is going to be plus concentration changes of dP with time dt. And we have rate of the reaction. So when you write the expression of the rate of the reaction, we need to consider the stoichiometric coefficient, right? So we can write the rate of the reaction with respect to the reactant, and we can also write it with respect to the product. How do we write it? It is 1 by x. You take the reciprocal of the stoichiometric coefficient minus dr by dt, and that is going to be equal to plus 1 by y, concentration changes of the product, dP by dt. Okay, so this is the generalized expression of what we discussed yesterday, based on which there was a homework also given. So please revise whatever we have learned every day. So this is the summary of yesterday's class. Also, we did discuss that whatever the type of rate is, whether it is disappearance, appearance, or rate of the reaction, it is always going to be positive. Always positive. And this can be determined only for the reactions that proceed with moderate speed. Reactions that proceed with moderate speed. Okay, so this is what we learned yesterday. Now today we'll build up on this. So after each and every session, ensure that you write and summarize whatever you have learned, all the formulae, important notes on a separate sheet of paper so that it will be useful for your revision. Okay, so this is a summary of session 1. Now, I had given you a homework, right? Let's try to solve that. What was the question? Were you able to solve? What was the question? For the reactions, so there's a typical reaction which is given to you. The rate of equation can be expressed as, and they have given two relations. Now the relations are based on N2O5, which is there on the reactant hand side, and NO2, which is there on the product hand side. The question is to find how is K and K prime related. Okay, so based on what we know, what can we do? We can write the rate expression of the reaction, correct? So let's do that. Rate of the reaction is equal to, so we have only two species which are given in the question. We'll write the rate expression based on these two species. Okay, so with respect to N2O5, how will you write? The stoichiometric coefficient is 2. Rate of the reaction should consider the stoichiometric coefficient. So it's going to be 1 by 2. minus of dN2O5 by dt. Correct? This is equal to, and what is the rate expression based on NO2? It's going to be the reciprocal of its stoichiometric coefficient, which is 1 by 4 plus dNO2 by dt. Correct? Now, please look at this. Already it is given that minus of dN2O5 by dt is KN2O5. So this can be substituted over here. Correct? This can be substituted over here. So what can we write? We can write it as 1 by 2. And from the question, it is given that this expression is KN2O5. So we write it as K times concentration of N2O5. And that is equal to 1 by 4. Changes of NO2. Changes of NO2 with time. And that is equal to K prime N2O5. So let's write K prime N2O5. Correct? Now, N2O5 is common. You can cancel that out. And here there is a 2, here there is a 4. I can cancel and write it as 2. If I rearrange this, what do I get? K is equal to K prime by 2, or 2K is equal to K prime. Option B. Option B is the right answer. Very easy. We just need to write the rate expression of the reaction, substitute whatever is given, and then we can rearrange and get to the final answer. Very easy question. Okay, so I'll give you a similar question in the assignment as well. Okay, one more question. Question number 4 of chemical kinetics. Question number 4. All right, so let's write rate of formation of SO3 in the reaction 2SO2 in gaseous state plus O2 in gaseous state gives 2SO3 in gaseous state. Now remember, this reaction was there in one of the questions yesterday as well. Okay, what is the name of the process? Contact process. Contact process. First question of yesterday's class or the previous session. Okay. So this is how we learn from questions. Now 2 times we did see that 2SO2 plus O2 gives 2SO3 and the name of the process is contact process. Okay. So now whenever in question papers, even if they don't give you the reaction, if they just mention the name of contact process, it should come into your mind that contact process is the place or reaction where SO2 reacts with O2 to form SO3. And you can do the balancing by your own. That's fine. Okay. Complete the question is. So the rate of formation of SO3 in the contact process ka reaction is 100 grams per minute. Question is rate of disappearance of O2 is option A, 50 grams per minute. Option B, 40 grams per minute. Option C, 200 grams per minute. Option D, 20 grams per minute. Mark this question as important. Why? Because, see, one thing is this type of question has not been asked in CSIR, NET or JAM. So this question was taken from a previous question paper of JEE. But it's a very good question. You can expect such questions. So please read the question and I'll tell you what is the twist in the question. Rate of formation of SO3 is given. And can you see it is given in the units of gram per minute? That is what you have to focus upon. We said in yesterday's class that the expression of rate, whether it is rate of disappearance, rate of appearance, or rate of the reaction, whatever it is, rate is changes of concentration of whatever species with changes of time. Correct? And the changes of concentration is either written in terms of moles per liter per second or in terms of atmosphere per second or bar per second, etc. So the changes of the concentration should actually be written as moles per liter per second over here, or moles per liter per minute. That is also fine. Any units of time. But here, they have given in terms of grams per minute. They have given in terms of grams per minute. So our first task is to convert the unit. Very important. Convert the units. Now, how do you convert grams to moles? All that you have to do is you have to divide it by the molecular weight of whatever compound that you take. Let's do it for this one. I repeat, how do you convert grams to moles? If some mass is given, you have to divide it by the molecular weight of whatever species that we consider. Then you get the corresponding moles. For example, here they have said that SO3 is being formed. What is given? It's given that rate of formation of SO3. Now, what is the expression of rate of formation of SO3? In rate of formation or rate of product formation, you do not consider the stoichiometric coefficient. So it is just plus dSO3 by dt, right? And this is equal to 100 grams per minute. We need to convert this grams to moles, for which you have to divide it by the molecular weight. Now, what is the molecular weight? Molecular weight is just the sum of the atomic masses of sulfur and 3 oxygen. So sulfur is 32 and you have 3 oxygen. 1 oxygen has got a mass of 16 units. So 16 into 3, 48. So the total weight is going to be 8 plus 2, 10. 4 plus 3, 7 plus 1, 8. 80. Okay, so it's going to be 80 grams per mole. The weight is going to be 80 grams per mole. Now you have to know that sulfur is 32, sulfur is 32, oxygen is 16. The masses you have to know. Gram per. Okay, so this is the unit. Now what do we have to do? We have to divide this grams with grams per mole, correct? So what do you get? Gram divided by grams per mole. Okay, so this gets cancelled and whatever you get is in terms of moles. This goes up and it becomes in moles. And that is what we want. Correct? See, we need it in moles per liter per minute, not in grams per minute. We need it in moles per liter per minute, not grams per minute. Okay, so let's do that. So in order to convert 100 grams per minute divided by 80 grams per mole is what you have. Now we'll cancel grams and grams. 100 by 80 is 10 by 8. And moles go per mole. When it goes to the numerator, it becomes moles. This is per mole. When it goes to the numerator, it becomes mole. So it's 10 by 8 moles per minute. Is that the unit that we want? See, we need moles per liter per minute. But we have got only moles per minute. Liter is missing. The volume is missing. but they have not mentioned anything about the volume in the question. So what do? We assume that the volume is 1 liter. We can solve such questions only through practice. Don't get scared or don't be panic when you see such new questions. So we do practice a lot so that we can rewire our brain in such a fashion that even when we get new questions that we have not practiced before, our brain can signal in such a way that we can think, tune, collect all the formulas and concepts that we know, and then come to the answer. Okay, so that is the purpose. So I know this question is slightly different from the earlier questions that we have done, but mark it as important. I'll put one more question in the assignment for you to practice, and you will be able to do it very smoothly. Okay, so what is it that we have done? Whatever rate of formation which was given in grams per minute was converted to moles per minute. How did we convert it? We divided it with the molecular weight of the particular species, SO3. That's it. Now, what we required is moles per liter per minute. As volume is not given, we'll assume that the volume is 1 liter. So it does not matter. Even if you write moles per liter per minute or moles per minute, it is the same. Why? Because the value of volume is 1. It does not matter. It does not matter even if you divide it by 1. Okay, so this is done. What have we got? We got the formation rate of SO3 in moles per minute. Now, what is the question? Question is to find the rate of disappearance of O2. Okay, so they have given the rate of formation. Now we have to calculate the disappearance of oxygen, for which we need to know how are they related. Let me take this reaction. This is the reaction which is given. Who are the candidates? SO3 and O2. We need to relate them. So in order to know the relation, just like the previous question, we'll write the rate of the reaction. What is the rate of the reaction? With respect to O2, it is minus dO2 by dt. And with respect to SO3, where there is a stoichiometric coefficient also, it is 1 by 2 dSO3 by dt. Right? Okay, now what is this? dSO3 by dt is the rate of formation which we already have over here. We have converted the units, and minus dO2 by dt is the rate of disappearance, which is the question. So how are they related? How are they related? Minus dO2 by dt is equal to 1 by 2 times the formation. 1 by 2 times the formation. Right? Now, formation is how much? 10 by 8 moles per minute. And when you solve it, you get that the disappearance of O2 is equal to 5 by 8 moles per minute. It's okay even if you don't write per liter, because we have assumed that the volume is 1 liter. So it does not matter even if you divide it by 1 or not. Now let's come back to the option. Do we have an option where 5 by 8 is there? Do we have an option where 5 by 8 is there? Please check the units. Units are in grams per minute. Units are in grams per minute. So what do we have to do? Whatever we have got corresponds to the number of moles of oxygen. We have to convert it. So earlier, what we did is we converted grams to moles, right? We converted grams to moles by dividing it by the molecular weight. By dividing it by the molecular weight. Now we have to convert moles to grams, because in the options, what you have, is in grams, but the answer that you have got is in moles. So you have to come back to grams. So here, if it is divided by molecular weight, here you have to multiply it by the molecular weight. Very basics. Okay, this is what we'll do. So this is equal to 5 by 8 into, what is the molecular weight of oxygen, O2? One oxygen is 16. So when you have O2, it is going to be 32. 32 grams per mole. Okay, I'll write along with the units so that you don't get confused. So we have 5 by 8 moles per minute into molecular weight is 32 grams per mole. Correct? Always practice questions by writing units along so that you won't make any mistakes. See, mole per mole cancelled. So there is 8 over here, 32 over here, 4 times. So 5 into 4, 20. And what do you have remaining? There is grams and there is minute. Per minute. 20 grams per minute. Is there an option? 20 grams per minute. Yes. Option D. Option D. Okay. Very easy. Very, very easy. You have to be just careful of the conversion. You have to know that if you want to convert a mass which is given in grams to moles, you have to divide it by its molecular weight. And if you have to convert your moles to grams, you have to multiply with your molecular weight. Now, if this is something which is entirely new to you, do practice questions. Okay, and that will make things much, much, much better. Okay, all right. So now we'll stop the questions. We'll come back to concepts. So please write the heading, Law of Mass Action. Law of Mass Action. Law of Mass Action. Okay. So we have already learned the way by which we can express the rate of a reaction. In law of mass action also, you express the rate of the reaction. Okay. So if you want, you just note it down here. Rate of the reaction ROR. Rate of the reaction ROR is proportional to the active masses of the reactants. I'll explain. You please note it down. The rate of the reaction is proportional to the active masses of the reactants raised to some power. Raised to some powers which may or may not be equal to their stoichiometric coefficients. Which may or may not be equal to their stoichiometric coefficients. Okay, please note it down. Once you have noted down, let's write an example by which you can understand. For example, let's say that you have A times A plus B times B giving you some products. Okay. So according to the law of mass action, the rate of the reaction is determined. It is written as small letter r. Okay. So the rate of the reaction can be expressed in terms of the reactants. Who are the reactants? A and B. And how do we write it? You write it as rate of the reaction is proportional. It is proportional to the active masses. Active masses means concentration of A, reactant A, and concentration of reactant B. Okay? So what they say is rate of the reaction is proportional to the active masses of the reactants raised to some powers. Raised to some powers. Okay? So this is the generalized expression. If I want to remove this proportionality constant, what I will do? Sorry, if I want to remove this proportionality sign, I'll add a proportionality constant. So R is equal to proportionality constant K, concentration of A raised to P, and concentration of B raised to Q, where this proportionality constant has several terms. Okay, it is called specific reaction rate. It can be called rate constant. It can be called velocity constant. These are some of the common names that are interchangeably asked in the competitive exams. Okay. All right. So we have written the rate of the reaction, small letter r, which is equal to rate constant into the concentrations of the reactant raised to some power. Now, this is very important. These powers, what you see over here, P and Q, they have a separate name. That is, the sum of the powers, P plus Q, is called the order of the reaction. Order of the reaction. It's a new term, order of the reaction. I'll explain what that is. So we said that the rate is proportional to the active masses raised to some powers, and the powers sum. The sum of the powers are called order of the reaction. And if you take P alone, that is order with respect to reactant A. And if you take Q alone, that is order with respect to B. And if you want the total order of the reaction, this is going to be P plus Q. This is going to be P plus Q. Okay. Now, there are two cases. See, one case is where this P is equal to the stoichiometric coefficient of A and Q is the stoichiometric coefficient of B, like this. This can happen or this may not happen. Okay. So you have to understand that the powers of the respective reactants can be equal to their stoichiometric coefficient, and at times it may not be. It's not necessary that it is always A to the power A and B to the power B multiplied with rate constant, and this is the rate. No. There are reactions, there are situations where expressions like this also happen. But there can be cases where it is entirely a new number, some random number P and some random number Q. We cannot determine that by just looking at the reaction. We cannot determine the powers of the rate expression from the law of mass action by just looking at the reaction. This is something entirely derived from the experiment. It's an experimental value. Okay, P and Q. P and Q, both of these are experimental values. Okay, experimental value. Now, write some typical examples so that you can convince yourself about this P, Q, and how is it related to the stoichiometric coefficient. I'll just summarize whatever we have written. You have some reaction where rate is expressed in terms of the concentration of the reactants only raised to some power. And here I have taken P and Q. So the sum of the powers, which is P and Q, is equal to order of the reaction, and that is a new term that we will be discussing. Now, if you want the order with respect to A, that is just P. And if you want the order with respect to B alone, that is Q. The proportionality constant is called the rate constant. That's all. This is the law of mass action. Okay? You need not learn whatever I'm writing now. It is just for your understanding. Write down. This is just for your understanding. You need not mug up or by heart. Some typical rate law expressions. Some typical rate law expressions. This is just for your understanding, okay? 1. H2 reacts with chlorine Cl2 in presence of light to give HCl, 2 times HCl. And you know what is the expression of rate? Rate is equal to rate constant, concentration of H2 to the power 0, concentration of Cl2 to the power 0. Please note it down. Now look into the screen. The stoichiometric coefficients of H2 and Cl2, they are 1 each. But in the rate expression, their powers are 0. Which means this is not something that you can just look at the reaction and write. Like we did in yesterday's session or the previous session. We used to look at the stoichiometry and write the expression of the rate of the reaction. Here we cannot do it. This is experimental. This is an experimental value. Okay? So can you see here the powers and the stoichiometric coefficients are not the same. Now if I change this halogen H2 to I2, giving 2HI. Now experimentally, when the rate of the reaction was determined, rate of the reaction, you can write it as R. Okay, rate of the reaction. It is rate constant into H2 to the power 1, I2 to the power 1. So now this is an example. This is an example where the powers and the stoichiometric coefficients are the same. This can also happen. Okay. Now another example, let's say H2 plus Br2 giving 2HBr. Now you know what the expression is? It's very complex. It is rate constant H2 into Br2 to the power 3 by 2 divided by concentration of Br2 plus another rate constant into HBr. There is K1 over here, please write. Okay. Now can you see here the order or the powers that you have got is also fractional. It is fractional as well, while the coefficients over here are whole numbers. One more example. Let's say you have 2 times ozone, which is giving you 3 oxygen. And here the rate expression is rate constant, O3 to the power 2 and O2 to the power minus 1. What does that mean? The order of the reaction with respect to ozone is 2, while the order of the reaction with respect to O2 is negative 1. So this is a case where in the rate expression, it's not only the reactant which is present, there is the presence of oxygen also. Situations like this can also happen. Okay, so these are all complex examples 3 and 4. Simply what we are learning is, when you have some reaction, you can calculate the rate expression, wherein it depends on the concentration of the reactants raised to some powers which may or may not be equal to the stoichiometric coefficient. That's all. Okay. That's all, and I hope it is clear to you. Okay. Now, talking on this, as I said, there are two cases, right? There are two cases. One case is where the powers are equal to the stoichiometric coefficients. So our reaction was AA plus BB giving products. And this is case one, where P is equal to the stoichiometric coefficient of the respective reactant and Q is the stoichiometric coefficient of the respective reactant. So when they are equal, when they are equal, the order is equal to P plus Q, which is in turn equal to the sum of the coefficients, which is equal to A plus B. And this order, P plus Q, being equal to A plus B, is called molecularity. A plus B is called the molecularity of the reaction. That is sum of the stoichiometric coefficient. So such reactions where your order of the reaction and the molecularity of the reactions are the same. Such reactions where the order of the reaction P plus Q is equal to the molecularity A plus B, such reactions are called elementary reactions. Elementary reactions are very simple reactions which happens in just one step. Okay, just one step reactions. One step. There's only one step. You mix reactants, you get products. That's it. No intermediates. No intermediates. You simply mix them and you get the products. Okay. Now, I said that this case where the sum of P and Q or the total order P plus Q may not be equal to the molecularity. Molecularity is what? It is the sum of the coefficients A plus B. Such reactions are called complex reactions. Such reactions are called complex reactions. Okay? Such reactions are called complex reactions. So you need to know what elementary reactions are for moving into the next part of kinetics. Very simple. The sum of the powers, which is equal to the order, will be equal to the sum of the coefficients. That's all. Okay. Note down a question. Question number 5. This was asked. The order of a reaction is option A, 0, negative or positive. Option B, experimentally determined. Option C, unitless. Option D, always equal to molecularity. Always equal to molecularity. Okay. Take down the question and mark your right answer. So there are multiple answers which are correct. So this is MSQ. MSQ means multiple answers are correct. More than one answer may be correct. Okay. All right. So order of the reaction is 0, negative or positive. Is that statement right? Yes. We already saw certain examples. We saw that order of the reaction can be 0. Just add the powers. 0 plus 0 is 0. Correct? So order can be 0. It can be negative. It can be positive. It can be fractional as well. Okay. So that statement is right. Already I told you that this is not something that you can just look at the reaction and write. This is experimentally determined. That is also right. It is just a number. It does not have any unit. That is also right. Option D is it's always equal to molecularity. That's wrong. That is wrong. It's not always equal to molecularity. It is equal to molecularity for elementary reactions. It's equal to molecularity for elementary reactions, which we have already written over here. Oh. All right. Note down a question. Question number 6. Calculate the order for a reaction 2A plus B gives C. Okay. Try it on your own. So reaction is given. We have to calculate the order. Try. Rate of the reaction is equal to rate constant into, yeah, do the remaining. So they have given that there's some reaction, we have to calculate the order. Okay, so rate is equal to K into concentration of A raised to P and concentration of B raised to Q. The correct answer is you cannot determine. Cannot be determined. Why? See, if you have written rate is equal to K into A to the power 2, it's stoichiometry, into B to the power 1. And you have written that the order is equal to P plus Q, which is equal to 3, third order, then this is wrong. You cannot write it like that. You can write it as the sum of the coefficients as molecularity only if it is elementary. I repeat, only if it is elementary. So in the question, if they had given, calculate the order of the elementary reaction 2A plus B equal to C, then our order is 3. But as in the question, they have not mentioned whether it is elementary. You will not assume that it is elementary and write. The correct answer is cannot be predicted. Okay, cannot be predicted. Be careful with that. Oh. All right. Note down the next heading. Last topic of the session. Units of rate constants. Units of rate constants. So we did see that if you have a reactant, for example, if you have just a reactant A giving some product P, the rate is equal to rate constant, concentration of A raised to some power, which we don't know. Let's take it as N, and N is the order of the reaction. N is the order of the reaction, where we have only one reactant, okay? Okay, now let's take case by case. Let's say that N is equal to 0. The value of N is equal to 0, which means it is a zero order reaction. Zero order reaction. So if N is equal to 0, our expression will be R is equal to K A to the power 0, or any number raised to 0 is 1. So this becomes R is equal to K. Now what will be the unit? We know that the units of R, we already know, it is moles per liter per second. That is going to be the unit of rate constant as well. Correct? Why? Because K and R are the same. Okay, so for a zero order reaction, the unit is moles per liter per second. What if N is equal to 1? So our expression will be R is equal to rate constant into concentration of A to the power 1. Upon rearranging, we'll get that R by concentration of A is equal to rate constant. Now here if I have to write, the unit of rate is moles per liter per second. And the unit of concentration is, we know, moles per liter. Correct? Now, moles per liter gets cancelled. And the unit of K is just per second, per time. Per time. Got it? Let's do the next one. Let's say the value of N is equal to 2. So come on, speed up. R is equal to rate constant into concentration of A to the power 2. Upon rearranging, we get K is equal to rate by concentration of A square. Now, if I have to write the unit of R, it is moles per liter per second divided by concentration square. Concentration is moles per liter. It's square, 2 times moles per liter. Correct? So there is 1 moles per liter which cancels out. And when you take these towards the numerator, per liter becomes liter. So this is just mole in the denominator, and when it comes to the numerator, it becomes per mole, and this is second. I hope you know this, okay? 1 by liter can be written as liter to the power minus 1. Or if I write 1 by per mole, if I take it to the top, the sign will change as mole. Okay. So what is the unit? Liter per mole per second. That is the unit. Liter per mole per second. Now let's put N is equal to minus 1. Try. N is equal to minus 1. So what will happen? We'll write R is equal to rate constant K into concentration of A to the power minus 1. Right? And if you rearrange this, this can be written as K is equal to R by concentration raised to minus 1. If I take it to the top, it becomes R into concentration of A. This is equal to rate constant. What is the unit of R? Moles per liter per second. And what is the concentration of A? The unit, moles per liter. So this becomes, in totality, this becomes 2 moles. So mole square per liter square per second. Okay, so this is how you do. Now please derive the expression, the general expression. Let's say that you have order N. R is equal to K into concentration of A to the power N. Okay, so how will we write it? K is equal to rate by concentration of the reactant raised to N. What are the units? Rate is in moles per liter per second. Moles per liter per second. And concentration is in moles per liter, but it is raised to N times. It's raised to N times, right? So there is 1 moles per liter over here. And there is moles per liter raised to n times in the denominator. So when you take it above, a raised to m by a raised to n is equal to a raised to m minus n. So here we have moles per liter to the power 1 divided by moles per liter to the power n. So the unit becomes, the general unit becomes moles per liter to the power 1 minus n per second. Important. Okay, important. So it's going to be highly useful. So you can just try putting the value of n as equal to 0 if you want. So if you put n is equal to 0 over here, it becomes moles per liter per second, which is a unit of rate constant for zero order reaction. You have already written over here. See, moles per liter per second. So similarly, whatever is the order, this is the general expression. Yeah, you need not mug up. If you can derive from here, you need not mug up. Please do not get confused between 1 minus n and n minus 1. Don't make a mistake. So it's to be on the safe side, you can derive it from here. All right. So you can derive it from here so that you get the general expression, because you have a lot to remember. You have a lot to by heart. So it's okay if you derive. It will just take 30 seconds. Okay, so with this, I'll stop over here. We'll do a few questions in the next session. Please note down the homework. Find the unit of rate constant if n is equal to 1 by 2, n is equal to minus 1 by 2, n is equal to 1 by 3, n is equal to minus 2 by 3. Okay, do give it a try. Just substitute the values of n in the general expression. Very easy. And let's meet in the next session. Okay, thank you.